In this video, we are going to start to talk about the idea of limits. And the idea of limits is we're going to be talking about average velocity and instantaneous velocity. But to kind of step back a little bit to help these things make some sense, we're going to refresh real quick about the idea of slope. Slope is going to be kind of the underlying idea that's going to be kind of going on behind the scenes with this information. So in the past, slope was talking about a linear equation, and you referred to it as m typically in some sort of an equation, and that was your rise over run or your change in y's over change in x's. And then there was a formula. If you had 2 points, you were using this formula to figure out the slope between them, y2 minus y1 divided by x2 minus x1. And that subtraction finds the change in the y's, and that's difference, that subtraction finds the change in the x's. Well, that also is a rate. And that's the big thing, a rate of change. That's what we're going to be talking about and kind of referring to. So one other quick little thing that we got to refresh or make sure we're okay with is the idea that we're going to be talking about functions. And function notation is an f of x type of equation. Specifically, we're going to be using this one, and it has a meaning to it. It's going to be referring to the position function. And then we have one more that is v of t, or v at t, is your velocity function. Okay, so just because that stuff is going to come up from time to time, so we want to make sure that we're okay with the terminology that's happening. All right, first thing is average velocity. Average velocity is going to be defined by the change in position over the change in time, which is exactly this, change in your y's over the change in your x's. So your graph is going to have your y values related to position, and then your x values are going to be related to time. So that's going to be a little bit different than the idea of instantaneous velocity, which this is going, it varies from one moment to another. So if you apply the brakes, you don't have a constant stopping velocity. Every instant, it's a little bit different. So the idea of this is going to be the limit of the average velocity. So we're going to be using, kind of messing with this first idea, as T2 approaches T1. Okay, so we're going to squeeze it. So if I take this idea and we're going to turn it into an average velocity, it's going to look like this formula-wise. So our velocity, the average of it, is going to be our position function at T2 minus the position function, position value, and then divided by T2 minus T1. Right, so let's bring that in. So we have a rock that's launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from the physics states that the position of the rock after t seconds is given by this function. So our position function, and each of these pieces have meanings behind them. It's for a different time. The position S is measured in feet. When S equals 0, the corresponding to the ground, find the average velocity of the rock between each pair of times. Okay, so if we want to figure out what the average velocity is between these two times, we are doing S of 3 minus S of 1 divided by 3 minus 1. So if we take 3 and we plug it into this equation, right? So if we're looking at what is S of 3, we're going to be plugging 3 into this. I'll spare you the math on this, but we throw it in a calculator or do it by head, in your head, and you would get 144. which this is your visual right here, that this graph is this. So we have quadratic that's face down. And over time, this rock is not the position of the rock, but it is going to be its height related to time, right? So we can also look here that at 3 seconds, our time was 144. So we got a couple different ways that we can get this. Oops. So 144. So we're going to take 144 minus the position at time 1. So either we're plugging it in, we're looking at this graph, and we're getting an 80. So S of 1 equals 80. So we're subtracting 80. And then 3 minus 1. So if we plug that into the calculator, we do this math here, we're getting a 64 divided by 2, which is going to be 32 feet per second. Right? And then any different if we go to 2 seconds? Sure, again, we're talking about an average velocity. So given a different period of time, our average is probably going to be different. So this would be S of 2 minus S of 1 divided by 2 minus 1. So S of 2 is going to be right here at 128. Back to subtracting 80 divided by 2 minus 1. So that's going to get us a 48 over 1, or 48 feet per second. So as far as velocities go, we have 2 different velocities that are happening, right? When we go from here to here, we're just talking about a slope. So we're looking at that slope represents our velocity, our average velocity from 1 to 3 seconds. And so that slope, that rate, is 32 feet per second. But if we get a little closer, now we're looking at this, right? And that's 48 feet per second, which is a little bit of a better representation. Well, it depends on what you're talking about. But as far as average velocities go, that's all we're looking to do, right? We're just trying to find the slope between those 2 points, right? And then eventually, in the next video, we're going to be talking about instantaneous. How do we make that happen? So like, what is the actual velocity at 1? What is that instantaneous velocity? And we have some algebraic ways to do it, and then eventually some calculus ways to do it.